Welcome everyone to the first Live and Know Data Science seminar of the new academic year. We're delighted to have Dr. Mike Walmsley here from the University of Toronto. Apologies, I'm going to read through my notes. Mike obtained his doctorate at Oxford, where he developed an approach to galaxy classification that brought together crowdsourcing and Bayesian convolutional neural networks. He then undertook a PDRA in Manchester under Anna Scaife, before obtaining the position of Dunlap Fellow at the University of Toronto. He is the technical lead of the citizen science project Galaxy Zoo, and today's talk is titled Foundation Models for Galaxy Images. Whenever you're ready, Mike.
Hi, folks. Thanks for having me. Good to hear some British accents again. Like the intro says, I'm Mike. I work a lot on galaxies and why galaxies look the way they do. But I thought maybe to open, instead of talking really more about what I'm up to, I would just try to show you. So for the people online especially, you can go here and there's a little live demo of my work. But I'll just swap to this tab to show the people in the room. So Galaxy Zoo is a project that aims to measure the appearance of the visual morphology, i.e. the shapes, the spiral arms, bars, this kind of thing, of all the galaxies in the sky. And to do that, we use a combination historically of citizen scientists answering questions about galaxies, and then we train models on what they say to predict what they would say for the millions of galaxies that are just too many to show them. So on the right here is some real example galaxies from a major telescope, and we can filter them to our model according to our model prediction. So for example, we can find the spiral arms, find galaxies that have 2 spiral arms, find galaxies where they are, let's say, loose wound. Takes a moment for internet to load in, there we go. Or we could go the other way, and we could instead find, for example, galaxies that have strong bars. Bars are these kind of linear features that cross the middle of the galaxies. So creating this kind of measurements is the aim of the game, scientifically speaking. And what I'm showing you here is not the answers of our volunteers, it's the predictions of our models. And specifically, it's the predictions of one model that predicts all the answers to all the questions we've ever asked. And that turns out to be really important for having models that perform, not just kind of perform well at the tasks we're training them for, but that generalize well to new tasks. And that's kind of the theme for this talk is the kind of foundation models concept. So you guys are data science CDT folks. You'll have heard of foundation models. Very briefly as a recap, foundation models are trained on as much data as you can get, like scrape the entire internet kind of thing, and then serve as a foundation, hence the name, that can be adapted to new tasks. And generally, I'll shorthand these parts as, and I'll call them upstream or pre-training, in that kind of raw data part, and downstream, fine-tuning, task-specific application, this kind of thing for the second half. Why would you want to do that? The theory is largely driven by this sort of seminal empirical paper, neural scaling laws. And what these figures are showing is they're taking a transformer model, they're having it do next token prediction, and they're saying, well, as I increase either the compute that I'm throwing at it, the size of the data set, number of tokens here, or the size of the model, number of parameters, and I look at my performance, my test loss, where of course lower is better, not only do things get better as I increase each of these, but they get predictably and consistently better. So there's this very clear power law relationship that says, as long as I have enough of the other 2 variables, increasing any one variable will give me a power law improvement in performance. And this paper is originally by a kind of OpenAI research group in 2021, and you can sort of see the brains turning to be like, so you mean we just have to keep adding data and compute and parameters and the models will get rapidly better? And that pretty much underlies, in short, the last few years of LLM work. What is really surprising maybe about these figures, if you're computer science orientated, is what's not on here is the architecture itself. So in this experiment, they played with different widths, depths, kind of hyperparameters of the network. But it just turns out to be more generally true that as long as you have a reasonably flexible architecture, it doesn't really matter how you arrange the parameters. The crucial part is simply these free variables. That's a little bit short, but that's the high level type. Downstream, the same thing can be true. And here I'm going to look at vision. So that was in the context of large language models and token prediction. In astronomy, we have a lot less language and a lot more images. So that's kind of the vibe of this talk, but many of the principles are the same. So in this figure is looking now at the downstream adaptation of foundation models for the vision task. And the pre-training part is on JFT 3 billion, so essentially a very large web-scraped data set. And the downstream application is to Imagenet 21K. And I do find this kind of funny because Imagenet used to be the pre-training data set on which you then adapt to new things. But now it is the small downstream data set that we're testing here. And these authors, Zai 2022, essentially looked at, well, if I take different size vision transformers and different size downstream adaptation data sets, how well do I perform as a function of those variables and also on the x-axis of my compute? So really the same three variables we had in the last plot. And what you can see again is you have this sort of predictable performance. Here they're calling it like the sort of optimal frontier, where if I have large models and large data sets, I do well. But if I restrict either one of those parameters, then I fall off this optimal frontier. So for example, if my adaptation data set is too small, if my models are too small, then I don't stay optimal. So the core idea here is that if I have a large pre-training data set and a large model, I can adapt very efficiently to different downstream tasks in vision. Now, for astronomers, that should really raise some eyebrows. And I understand in this audience, people are generally interested in data science for science, let's say, rather than astronomy specifically. But I think a lot of these principles would apply to any kind of foundation model work where you want to apply it to images that are qualitatively different to the kind of classic Instagram, Imagenet, JFT kind of terrestrial data sets. Because it's a fair question, and the question that I really wanted to address in the first part of this talk, does all of that actually work for astronomy, where the images are just so different? I already showed you a few examples, but you'll notice through this talk that images of galaxies are generally very low signal to noise. They're on a black background, essentially. They have a complete lack of perspective. They're sort of the opposite of egocentric vision, if you've heard of that, where someone is going around pointing a camera specifically at things for composition and so forth. Or perhaps it's like a Google Glass on your eyes or the new Ray-Bans. So lots of reasons astronomy images are quite different. Does this still work? In short, yes, but with some caveats, and I'll step through it. So in this recent paper, I wanted to just do the very simple test to say, can we reproduce these scaling laws in astronomy? And the setup is like so. We're going to train the biggest models we can on the largest data set we have in astronomy. We're going to see how well they do in pre-training, the upstream part, and how well they do downstream. And we'll compare that to training directly on the downstream tasks from scratch. On the left is a figure just summarizing what's been done before in the literature before this work. So here on the x-axis, the size of the data set, number of labeled galaxies. This is kind of in a supervised context like the previous slide. And on the y-axis, the size of the model in number of parameters. And each blue dot is a previous paper looking at training models to answer visual galaxy questions. This right box is the scale we're going to explore in this work. So out of order of magnitude larger in sample size and sort of the second largest models that have been trained. And then we'll apply it downstream in this much more common regime, because ultimately we want to build systems that work downstream at the kind of scale that astronomers have data sets for, which is typically of the order thousands to tens of thousands. Interestingly, as a sort of side note for the data science vibe, notice there isn't much of a relationship between the size of your data set and the size of your model, which I found kind of fun. Astronomers may be a little unconventional in choosing their setup. Here's the data set that I used. The details, maybe if you're astronomers, I've left them, they might be interesting. But in short, what we're going to do is we're going to take about 800,000 images, about 107 million human annotations, because we have many annotations per image, from a set of modern telescopes. These were labeled in the course of about a decade by Galaxy Zoo volunteers. Some maybe an order 100,000 volunteers, a lot of people. Now, training across all these data sets is not that trivial. And I'm going to just duck into a little kind of statistical aside for how we manage to stick these together in a way that's consistent to train one model across all of these tasks. You can imagine that for language, it's a next token prediction is a very generalizable kind of loss function. It doesn't really matter what the tokens could be code, it could be English, they could be other languages, as long as you have some choices in how you make them tokens, you're just predicting the next token. But for the supervised case, it's a lot less trivial to do this kind of sticking data sets together in a meaningful way in order to get one really large data set. So as a math aside for how we did that, the key is we use this loss function, which essentially only matters if volunteers had answered the question and takes into account how many people have answered when deciding how much we should or shouldn't penalize the model. So in short, we're gonna treat the idea that we've asked n volunteers, say, is this a spiral, and had k responses back, say, yes, it's a spiral, as having n trials and k successes. So that sounds a lot like a coin toss kind of problem. We know how to model biased coins with a beta distribution. And we know that if we toss a coin, we have a binomial distribution. I tossed it n times, I got k heads. So we're modeling the bias of the coin as a beta, we're tossing it as a binomial, and then we have a loss function that says, given its bias, and given how many people we asked, how surprised should we be that k out of n said yes? Nothing really sophisticated there, except that it means if we asked 0 people, and 0 said yes, the log likelihood is 1, the gradient of the loss is 0, and therefore it has no effect on the model parameters. And that makes it really easy to just treat all of our supervised labels as this long vector of where each kind of vector index is we asked n people and got back k answers. And then we can combine quite trivially all these different supervised labels. And I'll just mention as well this, I've talked through it in words as kind of a binary problem, but actually it does, none of this has to be binary. We just swap the beta for its multivariate version Dirichlet, binomial for its multivariate version, which is the multinomial distribution, and we can do just the same, somewhat more effectively and more computationally efficiently for a multi-answer context. So we have our data set, and we have a loss function that can handle taking different numbers of answers from different numbers of people and treating those in a noise robust way that allows us to seamlessly handle if no one was asked this question with this telescope. And then we train our models, and we wait. It took about 3 months real time to train our models, and this is the results. So in short, we see much the same scaling laws that Kaplan 2021 saw. So here I'm showing, again, test loss will pretty much always be on the y-axis, lower is better. On the x-axis, the size of the data set, so the number of labeled galaxy images. And each of these columns is a different kind of architecture. And I've chosen a range of kind of the classic res nets, efficient nets, through to more modern, for example, these sort of modern convolutional networks, modern transformer hybrids. But regardless of the network design, first big result, adding more training data gives us these power law scaling results. Then that adding more data is much more important than than the model size or the architectural choice. That said, model size does matter, as Kaplan found as well, but only in some cases. So in this next slide, I'm showing the number of parameters on the x-axis instead of the number of galaxies. This left column is showing if I use a quarter of my labeled images, about 120,000. In the right panel, I'm showing if I use the full labeled data set, about 500,000 for training. And each color is a different family of architectures, and then the way you are on the x-axis is how big the model is. So you can see that when I use the smaller labeled data set, making my models bigger doesn't particularly help. My loss is kind of the same as the models get bigger. But when I increase my data set size here to the largest one that we could have, increasing the model size is useful at test time, but only up to a point. You can see we're improving, and then somewhere around 200 million parameters, we hit this saturation, where for any of the architectures we tried, adding more parameters than that doesn't help. So you can't just keep adding parameters. And in Kaplan's framing, you'd say that we're now bottlenecked by the data set size, and therefore just continuing to increase the other part doesn't help. Breaking it down by question. So remember, we're asking volunteers many different questions about each of these galaxies and with each of these telescopes. We can see that for adding training data, the performance improvement we saw, that power law improvement, is not an average improvement. It's not like sometimes some questions we do better, some questions we do worse, but on average we get this power law. It's actually true individually for every question. So for all of the questions that we asked the volunteers, for a bunch here, I'm showing 3 large modern models, we're consistently improving individually on each question. If I make the models bigger, in contrast, I don't see the same thing. So for some questions, making the models bigger is very useful. For some questions, it doesn't really help. My kind of theory for this is perhaps questions that are more challenging, more visually complex, maybe that require a different kinds of spatial scales, might explain why some of these questions are improving and some of them aren't. For example, disk edge on doesn't really improve as we add more parameters. That makes sense because we're just saying, is this thing an edge? Is this thing essentially a kind of inclined blob, or is it not? You don't need 1 billion parameters to answer that question. But for some of them, like spiral arm, counting the spiral arms, it's actually visually quite hard, and perhaps makes sense that larger models could start to capture those details better. But headline point, adding images, labeled images, consistently gives us an improvement across every question, adding parameters only across some questions. That should probably not be a surprise, I think, to anyone here. You guys will know all about overfitting, and I think that's simply what's happening. If I compare the train and test losses for here the convex models, as I increase the number of parameters on that full 500,000 galaxy image data set, the train loss improves much quicker than the test loss, and eventually you get a pretty dramatic separation, which is classic overfitting example. So I think really the usual rules apply, and I put this slide in not really as a discovery, but as I suppose a note of caution that it's very easy to read a lot of hype around foundation models and hope that it essentially solves overfitting. But that's only kind of true in the sort of limitless data regime. And I think for scientific applications, that's often not the sort of regime we're working in. Turning on next to the downstream application, right? All of that was how well do we do at the pre-training task, the upstream, how do we classify this very large data set of galaxies? We can construct, I constructed some benchmarks, 4 different downstream benchmark tests, and each of these was designed to have a similar sort of a realistic astronomy problem at a scale which astronomers really work at. So these are 4 real data sets GWST is classifying galaxies on the James Webb Space Telescope, launched a couple of years ago by NASA, $10 billion, $15 billion telescope. Is LSB and which LSB are classifying whether galaxies have these faint sort of tidal features, these low surface brightness streams, and which LSB says, well, what kind of feature is it? And rings simply says, does this galaxy have a ring? Those are literally these ring-like features around the galaxies. On the right-hand side, I'm showing the performances on each of those sort of downstream benchmark tasks. And the key lines to look at in blue is if I train my model from scratch. In orange, yellow, kind of ugly color, is if I train on Imagenet. So I don't, instead of doing pre-training on galaxies, I do your traditional pre-train on the terrestrial images. And in green and red is if I do the full pre-training on the Galaxy Zoo Evo dataset that I introduced earlier, that 500,000 galaxies. And you can see that for all the datasets, we do quite dramatically better. So to compare, if we train on galaxies as our pre-training step. For example, the most dramatic one is LSB, where we go from needing order 10 to the 4 galaxies to do somewhat well, to doing much better with just 10 galaxies, because we can reuse the features we've learned from answering all of those galaxy questions before. So as a kind of piece of sort of Astro plus CS work, this is kind of a classic setup. But for scientists, maybe it's a bit unsatisfactory, because I, of course, created these benchmarks with the hope that I would be able to show results like that. It's kind of a constructed scenario. And the real test is actually benchmarks are cool, but can I use this to do science? Particularly, can I do science on tasks that I didn't know or anticipate when I put this project together? So for kind of the second half of this talk, I'm going to talk about really how we've been applying this to do a bunch of stuff in astronomy. But maybe I might pause for a minute and just see if people have questions on the sort of foundation model background.
I have one. You're looking at a lot of citizen science things.
Yeah.
You looked at the scientists, or sorry, the citizen scientists can also be thought of as neural nets that were trained on example images. Have you particularly the example images that are given as this is what a barred galaxy looks like, and just trained your neural nets on those to see, sort of, I mean, effectively, the citizen scientists may be being biased by a very, very limited training set that they're exposed to.
Yeah, I think that's a fair point. And broadly, we look in quite, it's not a topic really in this talk, but I can certainly chat more about how we try to compare the biases, let's say, of the citizen scientists. It's a kind of technical word. I don't mean it in a pejorative sense, but the way that different people will see different images and make different decisions. You're right, I think, to worry that the images we show people really matter. And actually, I spent a full year of my PhD designing what those images were. I'll just show you because I think it'd be useful for the talk. This is Galaxy Zoo itself. You can go galaxyzoo.org. And we actually use icons like this to kind of give people archetypal examples for what they're looking at. We give people a kind of a tutorial that walks them through the kind of images that we think they might see. And we also have these kind of help guides that you can pull out of the side that really goes in a lot of detail for what sort of galaxies you might come across and what you should say. So you're right, I think that people will learn from these images and we should worry about that. Equally, it's one of the really cool things about humans that we seem rather good at few-shot learning, in the sense that if you show people, a grid of 3 galaxies, they can be like, yeah, those are like, I don't know, maybe people here didn't know what spiral arms were. If I show you these 6 images, I reckon you could now do as well as most deep learning systems at finding more of these spiral arms. So in a way, that's their advantage.
It just sort of is whether those 6 images that were chosen,
Hmm.
someone chose those as being archetypal.
Yeah.
So technically, there's enough information in those 6 images to train your model on. But obviously that doesn't work. So it's
Yeah.
you know, is it possible to work out what? This is a bit beyond the scope of what you're talking about, but it's basically, if you were to train your model on those and give those much higher priority, would it do better because then it's being trained in the same data that the citizen scientists were trained on?
I would say unlikely, because I think that, so the model is trained on essentially all of these images and a further 492,000. They're not archetypal in the sense that they should be upweighted. They are typical examples, but I could have picked many, many other typical examples. I think it would be statistically unwise to weight these more. It's simply that we picked them to represent us like in a more of an active learning sense, I suppose, to represent a spread of the images that volunteers might want to see and recognize. But really, the full manifold of possible spirals is much more continuous than these 6 images, and I could have moved very slightly in that manifold left or right, and they should really be equally weighted near these images as well. But I appreciate the suggestion, and generally worrying about what the volunteers learn from is super important.
Yeah, okay, thanks.
Ryan has his hand up.
Hi, yeah. I just wanted to ask quickly, when you fine-tune the foundation model for the downstream tasks,
Yeah.
are you training like a separate smaller model to do that? Is it going through another separate neural net, or?
Yeah.
Oh, sorry, I don't know if you're muted or.
No, he is
I'm
muted.
sorry. My bad. Sorry, I didn't really talk through this on the slide, but the green and red lines are doing a linear fine tune, so keeping the model frozen and just changing the head, versus full, where we have a layer-wise learning rate decay that's pretty aggressive. But in principle, we change all the parameters.
Okay, cool. Thank you.
And headline point for all of these tasks, really, linear does just about as well. And actually, in practice, is a lot more robust. I find that for small fine-tuning tasks, it's quite easy to accidentally overfit your full fine-tune. But the linear one is much, much more robust. So actually, I tend to use linear in practice, and it works very nicely. And I will, in fact, continue to show off that now.
I'm gonna say, yeah, I could see it looks really good, actually. Cool.
Thanks. So actually, this is a perfect segue to the next part of the talk, because here is the kind of a UMAP. You guys will know what that is, your data science folks. It's, compression of the representation that the model has learned. Not a linear one, but the model's frozen, certainly. And if I click on different places in here, it will show the galaxies that have images close to that point on the manifold, a little like I was just talking about with the spirals. And I can select to know where should we click. Go up here, maybe. Let's see. Cool. So up here we have kind of disturbed merger-like galaxies with these bright arcs mostly. Right down here. These are kind of diffuse, clumpy dwarf galaxies, very star-forming blue ones. So what this visualization is hoping to communicate is that, back to your question, Ryan, the frozen model is learning to place similar galaxy images in similar places in the representation to give them a similar summary vector. And we can use that to build a bunch of science tools. So, by the way, if you want to try it out at home, as it were, then that's the demo URL. But a sort of practical use for that, this second URL, you can search, given a query galaxy, you can say, let's find some more. So we will attempt to demo this live, and we shall see what happens. So here is the sky from one of the telescopes that we you know, the model has been trained on. And I'm going to zoom in somewhere. Hope you'll trust that this is fairly random. In person, I like to have someone come up and pick a galaxy, but you'll just have to trust that I have no idea where this is on the sky anymore. And we'll pick a galaxy which looks kind of interesting and extended. They need to be reasonably, is a good one. They need to be reasonably bright because the model is only trained on the ones that have some morphology, right? Most of these blobs, it's just not an interesting test to do it. So here's kind of a pretty one. I'm just going to copy paste that URL into this sort of Streamlit web app. All that does is pulls out the coordinates from the URL. So it says the coordinates here. Then we wait for a minute, and what it's doing is looking up, it's finding the galaxy at those coordinates. It's finding the representation for that galaxy. It's then querying, doing a nearest neighbor search to find the galaxies that are most similar. So the galaxy that I picked is this one. We've snapped to the galaxy here, and here it's a kind of two-armed spiral with quite loose arms. And these are the galaxies that the model finds similar, which are all two-armed spirals with loose arms. So that's one kind of practical sort of similarity search tool for astronomers to play with. And I just have a bunch more examples. I won't go into that. We had a nice QA. I think I will move on to just talk about what else we can build on top of the representation, kind of that frozen representation. Given that similar galaxies are in similar places, what if instead of having a galaxy that I want to find more of, I don't even have one. I have 0 galaxies, but I know that if I see something, I'm interested in it. Like I know what I'm looking for. Maybe some kind of artifact or some weird merging galaxy or something like this. We can build a model just on top of our representation. So here I'm going to use a Gaussian process because it has this nice smooth kernel property that'll make it easy to make similar predictions for galaxies in similar places. And it also has a sense of uncertainty, principled uncertainty, which is very useful for doing active learning. And the setup is going to be, I'm going to show you a galaxy. You're going to say, are you interested in it or not? I'm going to train my Gaussian process to predict your interest as a function of where I am in the representation space. And I'm going to use active learning to pick the next galaxy to show you based on where I remain uncertain, plus where I think you are most interested. So really, it's a very simple recommendation system, but importantly, personalized to you, because I think it's not that hard in a CS sense to find anomalies, things that are rare, but things that are sort of statistically rare are not the same as things that are rare and interesting. And it's really the personal interest part that I want to focus on here, because, for example, cosmic rays hitting the telescope is quite a rare event, but it's not scientifically interesting to me, unless I'm a telescope engineer, in which case maybe I really do care about cosmic rays. So that's why the recommendation, the personal recommendation part is important. And shout out to Michelle Lochner and her astronomy work for really highlighting this. Here are just a set of beautiful, fun, weird, and interesting galaxies that a collaborator, Verlon Etzbeth, found in a telescope survey using this method. And if you want, there's a lot more quantitative details in that paper. Lastly, and for me, most practically, back to the core kind of downstream application part. We have these foundation models. How much data do we need to train them to do well on a new practical task that we did not have when we designed these models first? So that new practical task is a space telescope called Euclid. Euclid is going to survey a third of the sky to a resolution comparable to the Hubble Space Telescope, a little worse, but pretty comparable. And it's going to really transform, going to be 2 orders of magnitude more well-resolved galaxies than we've ever had. And so this is sort of the rubber meets the road moment for these foundation models, where now we have a ton of galaxy images to deal with. We are going to gather some volunteer labels. We're going to adapt the model and see how well they do. So this research project was just from this August, like 6 weeks ago. We ran this, really honestly kind of ruined my summer holiday plans. We took galaxies from Euclid that are available only internally within the Euclid consortia. But we made a deal with the Euclid consortia that said, look, if you want measured galaxy morphologies for your first data release, you have to let us show a very small subset of those galaxies to the volunteers first, so we can train our models. And they said, fine. So that's what we did. We took a month, we showed them to about 7,000 people. We labeled about 50,000 galaxies, about 1.5 million clicks, and we used that to adapt our models. And here I'm literally just going to show you the internal morphology catalog that we made, classic DF, and I'm going to just show you how a scientist might use that catalog. So for example, I might want to pick out all the strong bars. I might want to pick out all the galaxies that are merging. I might want to pick out the galaxies that have these beautiful tidal features. To volunteers, we call this major disturbance. Or maybe I want to do, and this is kind of a more realistic query, some sort of complex compound thing. Here I'm saying I want all the featured galaxies that are face-on, that do have a bar, and that are merging. So all the barred mergers. And this is just the random sample that comes out of that. And for the astronomers, you'll hopefully convince yourself that most of these are barred mergers. And from a computer science, from like a computer vision point of view, I don't think this is that, that much of a big deal, because people do much harder computer vision tasks all the time. But in astronomy, it's unusual, and there really is no non-deep equivalent to how you might be able to do this. There are no statistical measures for finding barred mergers, no sort of quantitative non-parametric approaches, for example. So in astronomy, this is, I think, quite useful, even if it isn't technique-wise all that complicated. And I'll just mention as well, it's not restricted to galaxies. It's also really good at finding different kinds of artifacts, problems with the images. So this is a problem that you get quite commonly in space telescopes called a ghost that we ask the volunteers to also label. So we're very good at finding these. So astronomers in the room, brief advert. If you do want to try these pre-trained models, they're all public, all the models are on Hugging Face, all the code is open. I've spent far too much of my life and my previous postdoc writing documentation for this. So hopefully it's easy to pick up, take away, and use, and quite a few other people have done that, and I've really enjoyed seeing some of the cool science that came out of it. So astronomers, if you're interested, you can grab it here. Non-astronomers, computer science people, what does this mean for foundation models in specific domains? Because I've pitched you a very particular view of the world here. I've said, this has all been in a very supervised context, going all the way back to that. Really, after the first slide, everything from slide 2 has been, we have a large supervised, at least weekly labeled JFT, say, data set. And I've argued that we can train foundation models, but only up to a certain size. So once I get to, here I have order 1 million images, and realistically in astronomy, there will never be more than 1 million labeled galaxy images to this level of detail, because labeling is slow. So no matter how we build our telescopes, the citizen scientists will only label so many things. So to first order, we have all the labels we'll ever have. Does that mean then that we're limited in model size? Once we get to models of a few 100 million parameters, that's kind of the limit for foundation models. In a supervised sense, I think probably. But more broadly, you guys all know that that isn't really how, outside of this presentation, people train foundation models, right? Foundation models are much more commonly self-supervised. Back to the Kaplan next token prediction, for example. In self-supervised, brief recap is you're just training to encode your inputs. So for example, predicting the next word requires no external label. The benefit of this is that by removing the need for supervision, you're only limited by the number of images, say, you can collect, which astronomers have worked really hard at for a really long time. We have a lot of images, and we're rapidly getting a lot more. But the catch is, it's not so easy to express what it is you want to find. So the explorations for this in astronomy, I'll just kind of walk through. This is the kind of timeline for foundation models in astronomy and CS above. So in computer science, we have sort of the foundation models paper I quoted at the start, the Kaplan paper, and we have a lot of clever vision stuff coming out like Dino, master autoencoders, etc. And then the last couple of years, I'm not even going to attempt to summarize this explosion in large models. In astronomy, we've had a bunch of different papers I won't dwell on because I know not everyone's an astronomer, but I'll just highlight that if I color them by being either supervised or self-supervised, really my ones are supervised or both, and everyone else's are self-supervised. So really that is arguably the main way that astronomers are trying to build foundation models. One sort of brief example just to ground that is from Stein 2021, where they used a simple kind of contrastive approach. They take the images, they give them two different augmentations, transforms, and then try to train their encoder to predict the same representation for an image given two different transforms and different representations if these images are different. Classic setup. More recently, kind of a fun work for the last couple of years, AstroClip, kind of inspired by the CLIP CS models, which use essentially captions and images and attempt to encode them both to have the same representation. They're using instead spectra and images, treating spectra as kind of token by token sequences, much like captions. So this is a really fun idea because it lets you do stuff like, given a spectra, find me the image which has the most similar spectra, even if I don't know its spectra. So like, what image would a galaxy with this spectra have, for example? Now that kind of multimodal work is, I think, really scientifically exciting and useful. It's still early days, I think, for where that will go, just because if you really dig into the numbers in the paper, on a unimodal task, this kind of multimodal approach doesn't seem yet to do better than if you would just directly train on all the images or all the spectra. But it's a really fun idea, and I suspect it will become a really leading approach going forward. So we'll see. Now, I don't really know what ultimately this will all end up as. I've just done a very kind of quick review of self-supervised learning, and of course, there's 1,000 different versions of this. What I am willing to bet is that whatever we pick, we're going to need labels downstream, at the very least. And I think if we do that, we're going to need to use the models we train to help us annotate. I think historically, we've run labeling projects as a kind of, we have a large set of, let's say, images. We give them to our volunteers or our paid crowdsourcing workers. They label them, we train our models, we hope the models do well, we test them, hopefully life is good. But in the foundation model world, we're going to have high quality models much faster. You know, in the examples I showed, tens, hundreds, thousands of labels are enough to train good models. So let's use those models to try to help annotate. And in a final kind of demo, I want to show you guys this website, ze.walmsley.dev, that we're calling ZooTasks. And slightly tongue-in-cheek, I'm calling it a model in the loop, as opposed to human in the loop, annotation platform for citizen science. So the idea is that you can serve any sort of custom annotation interface, anything you can write in JavaScript and React, and you can have volunteers from the Zooniverse, the sort of citizen science platform that Galaxy Zoo runs. They can contribute to giving annotations and helping with your data, talking to one another. But as they do that, crucially, there's this back and forth with models. And I'll just kind of illustrate what this sort of AI first approach looks like. So here's the website. I can log in, and you can log in with your Google account. See if this works. Live demos are always fun. Once you've logged in, you see the list of tasks, and I'll show you. I'll go through this just in the last couple of minutes of the talk. I'll go quite quickly to show you the galaxy, each of these tasks. So first, galaxy description, we have an image. And instead of asking you to go through this kind of galaxy zoo question tree where we say, okay, it's featured, it is not edge-on, it does not have a bar, it does have spiral arms, they're quite tightly wound, it has maybe 3 arms, not quite sure. Is there a central bulge? Moderate. Are there any bright bumps? No. Is it merging? No. Anything else unusual? No. This process, it works, but is not the fastest. We can just say, well, here's the model prediction from what we've trained on so far. Do I agree? Yes, I think you got it right, except I think it might be disturbed, and I will press submit, and I'll get another sentence. And this sentence is simply some if-else statements and the model's prediction. So that's much, much quicker way to label galaxies at the cost of some bias from starting from the model prediction. Another task that I'll show you is the segmentation task. So we can have a galaxy we might want to draw on its spiral arms. So for example, here's a spiral arm, and here's a spiral arm. And I might mark on the bar as well. Here's the bar. Submit that. That's kind of neat, but let's plug in the model as well. So if I press show hint, I have our sort of segmentation models. This is just a simple unit, taking those annotations, predicting where the spiral arms are. And then I might want to edit that. So I can press spiral here, and I might say, well, actually, I think the arms they extend a bit further than that here. But over here, I don't think they go quite this far out. So let's edit that out. And ultimately, what I want to go with this is to have people be able to make their annotation by just drawing in general, like roughly the arm is over here, and have the model autofill where you're trying to get to. So to really connect those pieces together. And I'll just show you the sort of progress we've made towards doing that. This is really just an infra demo. The model, this is just on MNIST, and actually the model is terrible behind the scenes. But just to prove that we can do this kind of live interaction, if I make a number here, I try to do a 7. It thinks it's a 2. Is it right? No. I think it's a 7, etc. The model is a dummy, but the point is, as soon as I raise my cursor, watch where it says current annotation. I'm going to raise it now. I get my model prediction. So we have this live back and forth, unlike the previous examples where we pre-calculated what the models would have said. So I think that designing our annotation to take into account having these foundation models in the first place is going to really speed up how fast we can get annotations and then how good our models become. And it will hopefully become a virtuous cycle. So if you have a scientific task that would benefit from this kind of model, human in the loop annotation, then please reach out. Be very keen to work with you to think about what that could look like. And I'll just summarize with a few kind of wild hypotheses for where the astronomy foundation models might end up. I already talked and said that self-supervised is clearly the only way, I think, to overcome the data bottleneck. But I think it will be complemented by downstream annotation collection in an intelligent way, hopefully, with something like our human in the loop platform. I think going multimodal is another approach to solving the data bottleneck, because you can learn from a more diverse set of data, but it's still pretty early, and we'll see ultimately if the multimodal approach helps on any particular unimodal task. And more generally, I'm really excited to think about how we use these models to do science in ways that we just haven't before. So there are essentially almost no segmentation catalogs of galaxies, despite 100 years of work on the topic since Hubble. The kind of human effort required to make segmentation maps and use them is, I think, prohibitive without these models, but the models make it not just possible, but perhaps even trivial to get segmentation maps. So for example, every galaxy in Euclid. And I think having those representations also opens up a lot of possibilities in terms of, for example, recommendations for the things you're individually interested in that I demonstrated earlier. So just trying to think a little more out of the box, saying, given the kind of new tools we have, what kind of individualized science could we do? And lastly, I think we're going to have a lot of different foundation models. At the moment, I would say my models, they're called Zubot, are pretty much the only ones that have been used for science beyond the thing they're originally trained to do. But I think that will change quite quickly. I think other people will build and publicize versions of these that get taken up by other groups. And I think it might end up in a scenario where people have found that some kinds of foundation models are better for some kinds of general tasks. So time will tell about all that. But hopefully I think it's an exciting time to be a data-intensive science student and perhaps able to guide and lead the field in how these foundation models play out. And I'd be really happy to collaborate, chat, and work with you guys on any kind of computer science or astronomy explorations around that. So thanks very much for having me. I'm happy to take any more questions.
Thanks, mate. That was an excellent talk. Do we have any start with questions from the room if anyone has any? Fire them out.
I've got one small question. Would it be possible to use the very large sort of universe type simulations, which have probably thousands of galaxies in computer models, and use those as not for training, but just a sort of we can look at this in 3 dimensions and just sort of, use those as just to see, do people sort of manage the fact that galaxies aren't always edge on? Because you've shown a lot of really good examples, almost all of which by eye look like they're exactly edge on.
Yeah. Exactly, face on. Yeah, I know what you yes. So people have indeed used, you're totally right. They have used often what they call zoom-in simulations. So they're kind of 2 broad types of simulations. There's like a universe in a box simulation, which is like order millions of galaxies, or there's like detailed zoom-in simulations, which is like order 1, 10. It might be 1 galaxy per simulation, we run it 10 times kind of thing. People have used both. They've used the universe in a box kind of simulation to try to predict what sort of morphology we might expect in the universe and compare it to reality as measured by the models in both cases. And people have used the kind of detailed models more in the way you describe, okay, this is that, for example, if we take the galaxy and rotate it, how does our view of its morphology change? And so how do our answers change? Because at heart, all my models can do is measure what we see in the image. But if a galaxy has beautiful spiral arms, but it's edge on, we don't see it. And so we need to calibrate those, and you're right. People totally do use simulations to calibrate that.
Ryan, do you want to go?
Yeah, so just kind of like a follow-on from David's question there then. Could you, on the flip side, see simulation data as viable training data, considering, I've worked with the Eagle simulations, for example, when training like the foundation models I work with. Well, I'm trying to anyway.
Good luck.
And there's billions of particles in these simulations. So could you see it as viable training data to try and translate into real world observation, or do you think it's best just used as like a test bed and purely as a test bed when building a model?
It's a really hard question. I think it depends what you're trying to do. I think that with Eagle specifically, we've seen in a previous Galaxy Zoo project that Eagle galaxies do not look particularly realistic on average. They don't, in the detail of the morphology. It's not really what Eagle is for in many ways. It just doesn't quite have the resolution to give you the right distributions of bars and spiral arms and so on. And they tend to look kind of clumpy and blocky by realistic standards. So using that as training data probably wouldn't be that useful directly, but it might be useful as another way to escape the data bottleneck. You might accept to say, well, maybe these galaxies aren't that realistic, but we can construct very easily purely self-supervised tasks. So, predict the gas mass, predict the dark matter halo, this kind of thing. Maybe that could be a nice way to combine with some real images and just kind of keep extending that large training data set.
Yeah, thank you very much. And then I guess as a really quick follow-up to that, could you see in a multimodal foundation model, would one kind of data potentially bottleneck the other? Like if you had these bumpy looking galaxies in simulations and then you have a much nicer, higher quality images, could the model be biased in some way?
Plausibly. I think people's approach at the moment is sort of throw everything in and hope.
Yeah, yeah.
So yeah, totally plausible.
Cool. Thank you.
Hey, Andrea.
Hi. Great talk. May I ask for these very low surface brightness features like rings and streams and so on? They're very hard to find, and especially in archive data from older surveys. Obviously, Euclid has these very beautiful images. My question is, in practice, do you mix up data from different surveys, or every time you get new data, you just focus, for example, at the moment, you just focus on Euclid, or you augment with other data? And also, obviously, with Euclid, you might find features that you never seen before just because you didn't have that low surface brightness. And is there a scope for unsupervised learning?
Yeah, great questions. So the core concept really is to train on as much data as possible and then apply downstream to specific individual surveys. So we train on all the telescopes we could find and their low surface brightness features, and then fine tune and apply to Euclid. So in a sense, we're doing both. For the discovering new kinds of low surface brightness features, like that's super interesting. There is a project certainly within Euclid to find anomalies in Euclid images with unsupervised learning. I think it's more general than low surface brightness features. I don't know of a specific project looking at unusual kinds of LSB features, but I think that would be really fun to explore. And I think you're right to highlight as well that the unsupervised aspect for finding anomalies is also important too, right? This is all somewhat biased in the sense that it's built on the answers people have given. Maybe we certainly don't want to bucket galaxies. And I think that's what I hope to do with that frozen representation, at least, rather than doing, for example, which of the 4 types of low surface brightness feature is this?
Thank you.
If I may ask a question. So I really love Galaxy Zoo. In fact, there's been a few times now when I've just been bored and I've just jumped into it because it's really, really cool just to see different observational galaxies and just pick out certain features and you're helping do a science project.
Yeah, I've been training these models. Thank you.
One thing I did wonder though is that every time I give a label within this, obviously, if I'm not particularly a domain expert, being either a school kid or somebody from the member of the public who wants to pick out these features, is there any sort of double checking going on either by a domain expert or are the images sort of like recycled through to give you a sort of, I guess, if one image has gone through to people, does it have like a statistical distribution for the label that you give it?
Yes, exactly. They're recycled. So traditionally we show each image to 40 different volunteers, and that gives us our distribution of answers. And that's the K out of N part in the models, right? We show it to 40 people and 10 said spiral, one of whom was you, but you were wrong, but the others were right. And on average, 30 out of 40 said not spiral, and it's not a spiral. That's the kind of setup. Actually, as a final closing CS side note, I think it's more information theoretic appropriate to show many fewer people per image than that, because we'll get more noisy labels, but a greater diversity of examples. And to me, that might be better, but it does make testing success really hard. So there's this back and forth in the team one. So how many people do we show each image to?
Thank you.
Thanks for helping Galaxy Zoo. And thank you all for coming to the seminar. And do reach out if you want to chat more.
I don't see any more questions. Which we
Yeah, if nobody has any more questions, we'll thank Mike again.
Thanks all. See you around.